Hi everyone, I'm Benny from Drexel University, and this is my talk on inequality with balanced digraphs, which is joint work of my advisor, Doug Grunberg. Here's the abstract. If you read it, great. If you didn't read it, also great. So let's start with some key definitions. So we're going to fix a balanced multidigraph, B, where V is just a set of vertices, A is a set of arcs, and then psi is just a map from the vertices to the arcs. Psi is not that important for this talk. And then we say that D is balanced if the out degree of every vertex equals its in degree. So basically at any vertex, the number of arcs going into it equals the number of arcs going out of it. Then we say that D is balanced. So for the rest of this talk, we're going to be focusing on balanced digraphs specifically. We say that a subset of the arcs is acyclic if the induced subdigraph with respect to those arcs contains no cycles. So if we only look at the vertex, if we look at the graph that has all the same vertices as D, but just the arcs in B, we say B is acyclic if that contains no cycles. And note that we're looking at directed cycles because you'll see later that we need them to be directed. And then a two root of our digraph is just a vertex such that every other vertex can get to that specific vertex. And so now if we fix vertex S, then we say an S convergence is an acyclic subset of the arc such that S is a two root of that specific induced subdigraph. So basically, with those arcs in B, every vertex gets to S. And so for any natural number k of vertex S, we let gamma k of S denote the number of S convergences of size k. And so our main result is that this number does not depend on S. So no matter what vertex you start at, the number of S convergences of a certain size is always going to be the same. And before I give an example, we can also characterize S convergences in terms of sinks, in case that helps. And so we call that a sink is just a vertex with no outgoing arcs. So if there's any arcs adjacent to that vertex, they all go into the sink. And so we say that a subset of the arcs B is an S convergence if and only if S is the only sink of the induced subdigraph. That's just another way to basically define S convergences, in case that's helpful. But now let's look at an example. So we're going to consider this balanced multidigraph. You can check its balance. It's not too hard to look at. But so the following are all of our one convergences. So first we have B, D, and G because 2 can get to 1 through B, 3 can get to 4, which can get to 1 through D, and then 4 can get to 1 through D. And as you can tell, there's no cycles, and so that forms one convergence of size 3. We also have B, D, and E, C, D, and G, B, D, E, and G, and B, C, D, and G. And again, while if this was an undirected graph, this would be a cycle. We're only looking at directed cycles, and so this is not a directed cycle. And you can check those are all the one convergences. And so gamma 3 of 1 is 3, gamma 4 of 1 is 2, and gamma k of 1 is 0 otherwise. But now, based off of our theorem, these numbers should be the same no matter what vertex we're looking at. And so we can check the, let's say, the two convergences of size 4. We have A, D, E, and F because 1 could get to 2 through A, or it could go to 4 through F. 3 could use D to get to 4, and 4 could use E to get to 2. And again, it's acyclic. And also A, D, E, and G. And that is all of them. And so gamma 4 of 2 is the same as gamma 4 of 1, and similar for everything. Pretty cool, but we could actually generalize this result. And so we basically define an S preconvergence being an S convergence, except we drop the acyclicity requirement. And so the set of arcs could have cycles in it. And we like delta k of S, the number of S preconvergences of size k. And in case you guessed it, this number also does not depend on S. So again, no matter what vertex you're starting at, the number of S preconvergences of a certain size is independent of the root. But actually, we could generalize this even more. And so if we take any subset of the arcs, we're going to let sites equal the set of all cycles of the subdigraph. And so we're basically saying B is acyclic if the set of arcs is empty, and then cycles of A is the set of all cycles of D. It's a little confusing of a definition. The example will hopefully clear it up when I get to it. And so for any natural number k, vertex S, and subset of the arc Z, we like gamma k Z of S to have the number of S preconvergences B of size k that satisfies cycles of B equals Z. So now instead of either having an acyclic digraph or just any set of arcs, we're looking at a certain set of arcs that satisfy that their cycles is the set Z. And in case you couldn't guess by now, this number also does not depend on the starting vertex. And so again, if you look at this balanced multidigraph, and we consider Z to be the cycle 1A2B1, then the one pre-convergences that satisfy this. First, we have A, B, D, and E because everything can get to 1 and A and B are in the set. There's also A, B, D, and G, and A, B, D, E, and G. And the two pre-convergences are actually the exact same. And you can check that these numbers are the same no matter what the starting vertex is. And so our result basically generalizes to any set of cycles. Now you might be asking, this is a cool result, but like, what's the point? My advisor and I, we actually had no idea this was a useful result until after we proved it. But then we found it generalizes a bunch of things. And so first, if K is just the number of vertices minus 1, then the S convergences of size K are simply the spanning arborescences of D rooted 2S, where spanning arborescence is just a directed forest. And so it's well known that this number is independent of S. And so that's what I think I'm saying. Next, if we take like an undirected multidigraph, and for every edge we make two arcs, one going in each direction, and K is just the number of edges originally, then the S convergences can be described as the acyclic orientations of G with unique sig S. And our theorem again is saying this is independent of S. And this has been proven using hyperplane arrangements and has other proofs. And so our result generalizes this result. And then finally, if D is weakly connected, then the largest K such that the number of S convergences does not equal 0 equals the maximum size of an acyclic subset of A. And computing this K is known as the maximum acyclic subdigraph problem for Eulerian digraphs, and that's NP hard. And then we can also consider the complement of an acyclic subset, which is well known in the literature as the feedback arc set. And so our gamma K of S counts the number of feedback arc sets as number of arcs minus K, and this problem is straight P complete. And I talked fast, so that's it.
Thanks, Benny. Do we have any questions?
One of the things you listed are evaluations of this thing, either way to type polynomial.
Yeah.
Do you know if any of your things you're counting are also evaluations?
Not to my knowledge, we haven't really looked into it yet.
We have time for other questions. I have a question. So you mentioned the screen Soslavsky thing was proved using hyperplane arrangements.
Yeah.
What is your proof combinatorial?
Yeah, our proof pretty combinatorial. It's a bunch of lemmas that do different things. We like at some point it's like a bijection between certain sets of arcs. We do a lot of counting in there. It's hard to like describe quickly, but like it's a lot of just different lemmas counting different things. And you put it all together and it proves the result.
Okay. Other questions? Great, thanks, Benny, again.